Hi folks, let's machine the feed ramp for a vibratory bowl feeder. Then let's add an Arduino with some code to custom count out screws. Welcome to another Wednesday widget. Let's cut up some raw material. We modeled up our stock as 2" by 3/4 by 6.3 inches. One of the cool things about this video is we're doing two different parts in the same set of soft jaws. But before we get there, we're trying out a new set of tall, built-in parallel self-gripping jaws. The folks at MMM USA sent these out to us and I think a lot of other people. What's interesting is comparing these against the Talons. These are very well built, they're beautiful, they're oddly tall to me, and I don't know if I've understood why yet, although they did do a good job of making sure their brand was laser marked. I laughed as I was filming this and I thought, huh, that was actually pretty smart of them. Let's see how they hold up here though as we rip off some material. Setting our work coordinate system in the top left of the part with the Heimer. We've actually got a fair amount of material to deck off. First cut, relatively gentle. Take a look at the second pass though. Jaws are rock solid. We're running 2,500 RPMs, almost 2,000 surface feet, 5 thou per tooth, which is 40 inches a minute, 0.1 inch depth of cut. Rock and roll. This is awesome. I wish I didn't have to do this. We just didn't have anything thinner on hand that would work, and 1/2 inch thick stock. The next size down we had is just a hair too thin. Switching over to the shear hog for our good old 2D adaptive clearing. 4,000 RPMs, 13 thou per tooth, so that's 52 inches a minute. We have had good success running it this fast, especially when you've got good work holding. 0.2 inch optimal load, that's width of cut. 0.2 inch step down, leaving 5 thou stock. I continue to love this tool. It performs great, it takes a beating, and honestly, we don't change the inserts. They last almost forever. It's insane. So I'm sitting here watching this and I'm thinking, wait a minute here, it still has one more depth of cut pass to go. And I thought, I think that's going to be really close, maybe too close, and I didn't want to ruin these brand new jaws that we just got in. So I went back and I right click, edit the setup, stock. The stock is 0.1 inches offset from bottom. That means this distance to here is 0.1 inches. Just to check that, if I move it to 0, the stock goes to the bottom. We'll set it back at 0.1. The lowest I'm going with my 2D adaptive is slightly below the model, and I can see that under heights, model bottom, -10 thou. So if I've got 0.1 inches of stock, and I'm going 10 thou below it, I have 0.09 inches. The jaw height on these jaws, the built-in parallel, is 0.08 inches. So I should have 10 thou left. Let's see if it works. Yep, we're good. It was really close. But 10 thou is 10 thou. So neither the shear hog nor 2D adaptive are finishing strategies. So we need to come back in and do some more roughing to get some of the material out that the shear hog couldn't get to. It's awesome. I love seeing those really fast sort of linking moves where it's wisping in and out of those, getting good chip evacuation, good cut quality. Our coolant's helping blow those out. Awesome. So we're doing a 3D adaptive clearing. We need to use the 3D because under Geometry tab, it has the rest machining. Rest stands for remaining stock. I always thought it meant for machine the rest of the part, but apparently it's remaining stock. And what that does is it's smart enough to realize that we've got to come in here and machine this nook and cranny and that corner as well. Just stuff that Shearhog couldn't get into. Max RPMs of 5140. 2 thou per tooth, and it's a 3-flute end mill, which means we're going almost 31 inches a minute. 0.035 optimal load. That's a hair less than 20% of the 3/16 inch tool diameter. Wanted to make sure we didn't, we had plenty of good chip evacuation, especially as we got inside of here, leaving 6 thou stock. We are taking it in 2 depths of cut here with the maximum roughing step down, just to make sure we don't overload the tool or snap it off. But you can see it did great. Make sure on any adaptive strategy, edit, linking, set the no engagement feed rate to as fast as your machine can run in the cut. And finally, coming in with the same 3/16 inch tool, 1.5 thou per tooth, or about 23 inches a minute to do our finishing cleanup. Super happy with how this part is turning out so far. Really happy with the surface finishes. And I was thinking after, as we were machining this, that I was wondering if the part that was remaining left on the floor would be too thin. It would affect the integrity of the part as we're machining it, but it was fine. So here's what's interesting. We switch our view over to the left side. I modeled them in the exact same place, which is not normally how I do it, but I did that because I wanted to use, again, the same set of soft jaws to handle Op 2 for both the left side as you see here, as well as the right side. Starting off on the left side with a 2D adaptive with the Shearhog. We didn't superfly it down because we've got this protrusion sticking up here. Any guesses what that's for? Kind of a creative use. I think it's going to work, but I've never done it before. So I forgot to set up tool 31 at the machine before I started this, and I don't want to go repost my code. So I hit stop. When you hit stop on the program in PathPilot, it rewinds to the beginning. So I went into T31 here, I set my tool height correctly, go back to the main tab, I hit reset, goes to the top, and type in find T31. Hit enter once, it jumps you down to the right point in your screen where that tool is first called. I can now right click above that adaptive operation and choose Set Start Line. Awesome trick in PathPilot. Now be careful when you start in the middle of a program. It is still a better chance than normal of crashing the machine because it may do a rapid move in a direction that you don't expect. It may not turn the spindle on. It may not turn coolant on. Things like that can happen. So really be careful, but nevertheless, cool trick that I didn't know until recently. So this 3D adaptive with tool 31, similar to like on the right side, just coming in to clean up stuff that the Shearhog couldn't get to. And actually the same thing yet again with tool 21, which is a 3/16 end mill to get into that small cavity. We've got to machine this 135-degree relief angle here, and I don't want to set the part back up to reposition it, so we will just surface it with a ball end mill and a parallel toolpath. Max RPM, 3 thou per tooth. The trick here is picking the chain of it as the containment zone or machining boundary and checking contact point boundary. Parallel toolpath with 10 thou step over. Should do a nice job of cleaning that up. The parallel toolpaths and the other 3D toolpaths, the blue lines often look funny, but if you go into simulate and you click on show points, it'll let you pick a point, and then you can scrub through the toolpath by clicking down your left mouse and dragging through it, and you can start to see the blue line is the control point of the center line of the tool, but in this case it's actually doing the cutting over here, so it starts to make sense as to why that tool path looks like it does. Coming in with a quick spot drill. And chamfer. And finally a 1/16 inch ball end mill, also using a parallel tool path to machine out this hemispherical pocket. Selecting the edge as the machining boundary, checking slope from 0.01 to 89.9, and 5 thou step over. What a great tool, especially for changing out jaws. We use every day. You want to make sure our vise is clean, and then let's throw in a pair of these monster jaws. I like this style because they're reversible, so we've actually already used the other side. You get a top and a bottom out of each one. And I like to tap them to make sure they're seated down. It's not that I'm trying to move it so much as I'm trying to check to make sure that it doesn't move. That way I know I installed it correctly. Finally, we've got to space them 0.27 inches apart. Why? Because that's how we modeled them. So if we take a look at our soft jaws, hit I, I'll pick this inside face, hold the control key, and click there. You can see those are 0.27 inches. Actually, Fusion doesn't always do a great job of showing you where the number is, 0.27 apart. Where do we set our XYZ 0? A lot of times on soft jaws, I like to do the inside corner, what would be sort of this corner right here. But because we've machined that part away, we're going to stick to the back left corner. Just be careful that you have the correct thickness of the jaw when you use that back corner. Machining the soft jaws, pretty simple. 2D adaptives to do most of the material removal with a 1/4 inch end mill, and then coming back with a 3/16 to do some contour cleanups and to machine that deeper pocket right there. We've had some requests for a video on sort of the guide to soft jaws, so that's on our list. Look for that coming up soon. We've learned some good tips and tricks, but the biggest thing I want to encourage folks is to use soft jaws. They're not particularly expensive, and they're definitely not difficult to make. I think Fusion makes it even easier being integrated CAD/CAM, so look for that video soon. The other cool thing about soft jaws is our coordinate system doesn't change. It remains that back left, both as we made the soft jaw cam right here, and as we start our left op 2 and right op 2, those coordinate systems share that exact same point, so I don't even need to re-zero the machine, which is awesome, and it makes your parts more accurate. I machined the location in place. Grab our piece, kind of slide it in, make sure we've got a good fit and that it feels right, doesn't rock, clamp down, rock and roll. Starting off our right op 2 with a 1/2 inch roughing end mill. A little bit of a different recipe here. 2800 RPMs, 20 inches per minute. But we're taking a thin depth of cut and a greater width of cut. One of the reasons we're using the 1/2 inch roughing end mill instead of the shear hog is I love the shear hog, but it can be a little bit of a violent tool. It works great when you've got super rigid and really secure work holding. And these soft jaws ended up performing really well, which I'd hoped they would, but I wasn't sure at first. So I thought, well, let's just try it on the 1/2 inch rougher and see how it goes. After we deck it off with that adaptive, we do a 3D adaptive and rough out the rest of this. and then a horizontal just to clean up the surfaces after all that roughing, get a little better surface finish. Tool 31 adaptive to get our trough machine out. .2D contour to clean up the surfaces. Spot our holes. And now we've got to machine the other part of that little feature. We're going to start with a 1/16 flat end mill and an adaptive strategy. A square shoulder end mill's got much better surface footage, so it's easier to take cuts with it than a ball end mill where the center part can end up loading up or tearing instead of shearing the material. So max RPMs for sure. Taking it easy, only 7/10 of a thou feed per tooth, so that's still actually almost 11 inches per minute. Really small optimal load or width of cut of 15 thou, maximum roughing step down of about 0.05. You can see our toolpath though is going to remove most of that material, and then we'll come back with our 1/16 ball end mill and clean up the bottom of that first surface. We had a similar 3D feature, that 135-degree angle on this side of the part. And I kept this incomplete operation just to show you guys a really cool example of two different toolpaths. Select them both. So I'll click the first one, hold Control, click the second one, right-click, compare and edit. What's different? There's one feature that's different, contact point boundary, that's changing those two. I kept this one here to remind myself to show what it does. So if I edit that and select contact point boundary, which limits the cut position to where the tool touches rather than with the center, which is really great. It's basically trying to ignore the center line of the tool, but rather look at where the tool is doing work. That's going to give us the better tool path. In fact, the other one would have given us an incomplete tool path. Super happy with how that turned out after we fixed the contact point boundary. I'm trying to use less shop air, so we've got a foxtail next to our machines that we use to brush them off. Looked great. Softails held up great and held the part really well, so that's a win. Throw in our next part. Same thing, like kind of lightly press down as I screw the vise in, and then I'm tapping it not so much to seat the part, but to check to make sure it doesn't move when I tap it with the hammer, because if it does move, that means I didn't put it in there correct in the first place, or there's a chip or a problem in there. So when we start machining this, we've got to be careful. We first take a cleanup pass with a shear hog around the part. That way we're not left with a top hat or unsupported material, which if we came through with a shear hog is going to tear up and definitely will rip the part out of the soft jaws and maybe destroy the Superfly insert. Again, look at the Superfly cut. It's amazing. 2,500 RPMs, 45 inches a minute. 0.1 inch depth of cut, no problem at all, and the surface finish is still excellent. That's what I love about it. Last two ops, we're using Tool 31, our 1/4 inch end mill, to do a 3D adaptive that's going to rough out this 3D surface. We're just trying to get most of the material out of there. That way when we come back with a parallel tool path with our ball end mill, it's doing more finishing work and less material removal. I don't need a perfect surface with this ball end mill here. You'll see in a second, it's just a curve along with the vibe bowl to give it a good fit. I should have patched that hole too. Click here for our video where we talk about making better 3D toolpaths by not having it dip down into what's supposed to just be a countersink or countersunk screw head. All right, let's go put it together. Let's tap a few holes and then let's see how it works on our vibe bowl. So we've got our two parts. We put them together like so. And this was our idea for that hole. We needed a small 440 screw there to mount the SparkFun photo interrupt, and rather than having to create a third setup, we did it this way, and it worked great, even when we tapped that in the drill. Here it is. So this is a vibratory bowl feeder. They are available, generally finding them at auctions or even on eBay. They're usually not too expensive, but they're really heavy, and they work by creating a vibration or a harmonic that causes screws or nuts or washers or just about anything to move up and around this bowl. And these are used all over the world in factories and in automation. There's really nothing else that does what they do. But to me, it's worthless unless I can output a known quantity. In this case, I want to be able to control how many screws. So we've got our machined parts. We're using a Noga arm that lets us actually conveniently mount it from the base of the machine, and that way we don't have to attach it to the bowl. It's an easy way to prove this out as a proof of concept, because once you attach something to the bowl permanently, it can actually change the way it works. So we added to it this SparkFun optical interrupt. We got an Arduino with an LCD screen, and this lets us, with a power tail device, that's a safe way to control AC, 110 wall voltage AC, to turn it on and off to get the screw count that we wanted. This is awesome. Let's take a quick look at the Arduino code. We've got the code commented out pretty darn well. A quick walk through it though. We're using the Adafruit LCD shield that's got those buttons on it, and that's what lets us increment up or down by either 1 or 10, depending on what button you push, and turn the machine on. Digital writing the PWR pin, which we take a look, that is pin 13. And that's what controls our power tail to turn it on or off. And we're using a switch state for the photo interrupter. So every time it counts a screw, that changes the state, it compares it to the last state, and it indexes it up 1. And as soon as the quantity it counts matches what we've set it to do, it turns the power tail off, resets the count, and we're good. We're super excited to have the new NYC CNC site up, so link in the video description to where you can go not only watch the video, but we've got the bill of materials listed out, and we've got the Arduino code pasted right here in a way that lets you copy and paste it right into your Arduino IDE and get going. Folks, hope you enjoyed. Thanks for watching. Take care. See you soon.